Okay, so let's get started. And there are two things I want to mention here. First of all, about the final exam. So I propose to do the final exam in next week, December 13th to December 15th. So there's a three days period of time from next Tuesday to next Thursday, so that I can grade it on Friday, and hopefully the final grade will come out by that time. So let me know if this does not work for you, and we can try to find some other time on that. But I think for these 3 days of period, it should work out. So the deadline is Thursday, 11:59 p.m. And everything will be pretty much the same as those two midterms. So this is about final exam, and the other things that I created an additional assignment for the course feedback. So for anyone that provides the course feedback will give a 2-point bonus, as I stated in the syllabus. So you just need to submit evidence of for this. You don't have to provide your course feedback to me. It should be anonymous. So you can upload the evidence as a picture to this assignment so that I can check it. And the last one is about today's office hour. Unfortunately, I'm not available between 1 to 3. So I will stay in the Zoom from 3 to 6 if you have any questions. Or if that does not work for you, you can always send me an email and we can find another time before next Tuesday. We can schedule a separate meeting to discuss the homework questions. Okay, so are there any questions regarding the final exam? Okay, if there's no questions, then let's continue our discussion on the random process. So this lecture will take a little bit longer time, but I will finish everything, and if you have another schedule after 10:30, feel free to leave, and I will record everything and upload to the YouTube channel. So as we discussed last time, we defined the random process xt is basically a sequence of random numbers that occurs over time. And so for every fixed t, xt is a random variable. It's a random variable. So we are looking at a sequence of random variables over time, and that is called a random process. Now, in particular, for this random process, we can look at its sample path. The sample path is that we fix an arbitrary outcome of your experiment, omega, from the outcome space. And then we look at the trajectory of the realizations of the random variables, right, in this random process. So we look at xt, the random variable at t. In fact, this is the realization of the random variable xt at time t, associated with the outcome omega. And this, we have such a realization for every random variable xt. So collecting this trajectory of realizations associated with a fixed omega, this will give us the so-called sample path. So you can view the sample path as a realization of the random process. right? Just like the realization of random variables, you have a random variable xt, and this random variable will map omega to a realization. And this is just a sequence of such realizations. And then we said that the complete way of describing the random process is to look at the joint CDF function of all the random variables involved in the random process. Because if we know the joint CDF, we can know everything about all these random variables. And then we started to define some very basic statistics of this random process. And they are pretty much the same as the statistics that we defined before. So the mean is basically the mean of the xt. And for every t, this mean is a fixed number. It's the mean of the random variable x at time t. So this is a time varying function of t. And autocorrelation basically describes the correlation between two random variables of this random process at two different times, s and t. And autocovariance is corresponds to the covariance of these two random variables at different times. And the way we have this example last time to show that the way to calculate this statistic is basically following the basic definition. To calculate the mean, you just need to calculate the mean of this random variable at a specific time. If you know the PDF or some basic information of this random variable, you can get its mean. And the correlation function is also basically calculating the mean of this product, the product of two random variables. Now today, we will introduce two notions of stationarity about the random process. Because the random process is a sequence of random variables over time, right? When we talk about sequence over time, or basically, for example, a signal over time, a time series signal, like an audio signal, video signal, we want to look at how stationary that signal is. Are there a lot of fluctuations in it, or is it like very simple and a very stable signal? So here for random process, we can also define some notions of stationarity. So we call a random process xt strict sense stationary, or we basically say SSS, triple S. Strict sense stationary if the following is satisfied. Basically, if this joint CDF function, okay, I'm going to skip all these statements, but essentially, if you look at the joint CDF function, this is a joint CDF function over multiple random variables involved in the random process, right? You pick some arbitrary timestamps, T1, T2 up to Tn, and consider the random variables at those times, right? So we have this many random variables, xt1, xt2, and xtn. Right? These are random variables involved in the random process at different times. And then you consider they are random variables, so we can consider their joint CDF function. This is the most general information about these random variables. And assuming so these we denote their corresponding realizations as small x. Now, such a random process is strict sense stationary if any such joint CDF function is invariant to the time shift. Now, what does this mean? This means that if you look at this joint CDF function of another set of random variables, well, these random variables are at the time steps that are shifted from these time steps by a constant tau. Right? So here we have T1, and here we have T1 plus tau. We have T2 here, and after shifting, we have T2 plus tau. So after a constant shift, we will get another set of random variables, xt1 plus tau, xt2 plus tau, up to xtn plus tau. So all these time steps are shifted by tau, the same constant. Now, if these two sets of random variables, they have the same joint CDF function, right? Then we call it strict sense stationary. Okay. Basically, if we draw a picture, now what this strict sense stationary basically says that, okay, suppose you have random process, now you pick arbitrary numbers of random variables. Okay, suppose this is xe1. So basically, this is time t1, and this is the corresponding random variable, xt2, xtn, and you can pick arbitrary number of them, right? So in general, there could be n of them, and then you consider time shift tau, an arbitrary time shift tau. This is tau, so this would be x t1 plus tau and this is xt2 plus tau. And this is xtn plus tau. Right. So you pick t1 and up to tn. This is the first set of random variables that we consider. And then we shift all these time steps by a constant tau. So now we are looking at these red dots. These red dots, they are corresponding to t1 plus tau, t2 plus tau, tn plus tau. And then we consider the random variables at those times. Now, strict sense stationary says that the joint CDF of xt1 up to xtn, which are the original random variables that you picked. This joint CDF is the same as the joint CDF of those shifted random variables, these red random variables. So basically, in one sentence, this is basically saying that the joint CDF of the random process is invariant to time shifting. Is invariant to time shifting. Yeah, no matter what this tau is, it is always the same. And you can generally, you can intuitively see that this is a very strong condition, because the signal that occurred at these random timestamps right? They could be highly random, and once you shift the timestamp to a certain amount, the signals occurred at these red points. They could be not that related to the original ones. So in general, in order to satisfy this strict sense stationary condition, the random process has to be very well behaved and very stationary. Basically, if you happen to know the joint CDF or all the information about these random variables, then you pretty much know everything about the entire random process, because you can kind of cover the entire random process by shifting this these points by a certain amount, and then you can cover almost the entire set of random variables in the random process. Okay. So this is a definition, right? If the random process happen to satisfy this condition, then we call it strict sense stationary. And because of this, for strict sense stationary random processes, we have many nice properties. For example, if we look at the mean function, then it is also invariant to time shifting. Because why? Because the CDF is invariant. So the mean, which is can be expressed as integration over the PDF, right? It is also invariant. So if you know, and because this tau can be arbitrary, right? This tau could, in this invariant definition, this time shift tau could be arbitrary. So we can simply choose tau to be negative t. So basically, this mean function, the mean of this random process, equals to such a constant. This constant is the mean of the random variable at time 0. So mu xt, the mean of the random process, equals to mu x0, which is the expected value of x0. Right. So this is the first property of the strict sense stationary random process. The mean, if you look at the mean of this random process, that should be a constant, a straight line. The mean does not change over time. And then we can also look at this autocorrelation function. Now, by definition, it is the expected value of this product. And we know that, again, following this invariant condition, the invariant condition says that basically, if you consider xt1, xt2, it is the same to consider xt1 plus tau and xt2 plus tau, because their joint CDF is the same according to this condition. Right? And because of that, the mean of this product equals to the mean of this shifted, equals to the mean of the product of these random variables, where they are shifted versions of the original ones. Right? So here we have t minus tau and s minus tau. And because tau can be arbitrary, now this tau can be arbitrary. So we can choose tau to be s, so we can get rid of s. It equals to x t minus s, because tau equals to s now. Xt minus s times x0. And this is something, this mean is only depending on the initial random variable x0 and the random variable at t minus s. So this is something only depending on, this is a function of t minus s, basically. So to summarize, the autocorrelation function of strict sense stationary random process is actually a function of this time difference. Right. This autocorrelation only depends on how far are these random variables are located. Only depends on the difference, time difference, t minus s. And in practice, such a random process, the strict sense stationary random process, is a very limited class. Most random processes does not satisfy this condition because it's too strong. Right? Such a invariant condition must hold for any number of random variables that you pick, and for any time shift. Usually, this is very hard to be satisfied. So this motivates us to consider the second wide sense stationary random process, which is a relaxed version of the previous one. Now, the wide sense stationary is basically removing this invariant CDF condition because it is too strong. But instead, we just look at these consequences. These consequences include that the mean is a constant, and autocorrelation function only depends on time difference. So these are the conditions that we are going to use in practice. So basically, we define that a wide sense stationary random process are those random processes whose second order statistics are time invariant. Now, basically, these are two conditions implied by the strict sense stationary random process. So let's look at this. Basically, it says that, okay, if the mean of the random process is a constant, and moreover, the autocorrelation function only depends on the time difference. If these two conditions on the statistics are satisfied, then we call it wide sense stationary. And we can see that this is the strict sense stationary implies wide sense stationary, because following the definition of strict sense stationary, we can derive these two conditions. Like here, we derive that mean is a constant and autocorrelation is only depends on the time difference. So SSS implies WSS, the wide sense stationary. This implies that one. But in general, wide sense stationary cannot imply strict sense stationary. And if these two conditions are satisfied, we can also conclude that the autocovariance function is also a function of the only depends on the time difference. Because the autocovariance function CXST is the autocorrelation minus the product of the mean. Minus the product of the mean function. Now, if this is, we know this is for wide sense stationary, this is only depending on the time difference. It's a function of the time difference. Here we assume t is bigger than s, right? Without loss of generality. And these are constants, right? For wide sense stationary, these are constants. So it is just mu x squared. And in the end, this is a function on t minus s. This is a constant. So it is a function. In the end, it is a function of the time difference. Right. So this is the key property of wide sense stationary. Right? The mean is constant, and all the second order statistics, including autocorrelation and autocovariance, they only depend on the time difference that we are looking at. And we already mentioned this remark. SSS implies WSS, but not the other way. Okay, now let's consider some examples regarding these stationary random processes. Consider such a random process. Well, the f is a constant. So in this random process, xt, the random variable xt at time t is defined in this way. It's a times cosine 2 pi ft plus theta. In general, right, this is a cosine signal. If you take 3500, the standard cosine signal, frequency f and phase theta, amplitude a. Now, why is this a random variable? Well, because for this signal a and theta, the amplitude and the phase, we assume they are independent random variables. Okay, so the amplitude and phase, they are random, they are independent random variables. The frequency is the constant. For example, this can be used to model that when you create this signal in the circuit, maybe there are some random noises injected into this signal, so that the amplitude is a noisy version of a certain desired amplitude, and also for the phase term. So we model these two as random variables. We assume they are independent. We also assume that the second moment of A is finite and almost A is bigger than 0 almost surely. Otherwise, this signal simply becomes 0. Okay, basically we are considering a cosine signal where the magnitude, amplitude, and the phase are random, and they are independent. Now the question is, under what conditions on A and theta is this random process wide sense stationary? Right. So to do that, we just need to find out the conditions on A and theta so that these two conditions are satisfied, right? The first condition is that xt has a constant mean over time. And then the autocorrelation is a function only depends on the time difference. So let's just look at these two statistics and see what kind of conditions do we need in order to satisfy them. So looking at the mean of this random process, it's basically the expectation of xt. Okay, now xt is this signal, so we plug it in to this expectation. Okay, now let's look at this one. This is a product of A and this cosine. Now in this signal, right, there are only two random stuff. One is A and the other is theta. And they are independent. But because of that, we know that A and this cosine part, they are independent. Because this cosine part only involves theta, and theta is independent from A. Therefore, by independence, we can separate the expectation. So the expectation of the product equals to the product of the expectation. Right? Independent implies uncorrelated. So the expectation can be separately calculated. So it's product of the expectation. But here we don't know anything about A yet. So let's just keep this term. So this term is just the mean value of A. So statistics of A. And here is the expectation of this cosine theta. And for this cosine function, we can expand it using the, we have cosine, we have this formula for cosine functions. And the formula is cosine A plus B, these two arbitrary numbers equals to cosine A, cosine B minus sine A, sine B. Let's use this one, we'll get here. And in this way, we are separating the frequency part with the phase part. And then this is, we can apply the linearity of expectation, right? So these are one term minus the other term. So we can take expectation separately. And for the first term, note that this part is a constant. There's no randomness in this part. And the only randomness is the theta. So the expectation is applied to this cosine theta part. And similarly for this part, the expectation applies to sine theta part. And this is it. This is the simplest form that we can get because we don't know anything about A and theta. I mean the PDF. So we cannot evaluate their expectations. But here we are trying to figure out under what conditions is this random process wide sense stationary. So we need this mean to be a constant. To be a constant. We need this function, a mean function, to be a constant. A constant means that it is a number that does not depend on t. It does not depend on t. If you look at this expression, there are two terms that depends on t. Cosine 2 by ft, sine 2 by ft. These two terms depends on t. So we need to impose some conditions on A and theta so that we can actually get rid of these two terms. Get rid of these time varying terms. So one is cosine 2 by ft, one is sine 2 by ft. In general, these two terms cannot be cancelled, do not cancel with each other, right? Because cosine, one is cosine, one is sine. They are different. They have different phase. So the only way we can make this stationary is to let these two coefficients to be zero. Okay. If these two are zero, then we can completely get rid of this cosine t and sine t terms. So we need these two coefficients to be zero so that the mean function, basically it is zero mean random process. That's the only way we can get a constant mean. Right, so this is the first condition that we identified. We need the expectation of sine theta to be zero and the expectation of cosine theta to be zero. Now this is a condition on the phase term theta. Now, theta is a random variable. So this is a condition on this random variable. And this is only about the first condition of wide sense stationary. We also need to look at the second condition, which says the autocorrelation is a function of time difference. Well, we start from the autocorrelation part. Now, xt times xs, well, plug in xt and xs. We get a squared cosine 2 pi ft theta plus theta and sine 2 pi ft fs plus theta. Here I believe it should be cosine. Right, so xt equals to a cosine this one, xx equals to a cosine. So this should be cosine instead of sine. Yeah, it should be a typo. Okay, so what happens next is again a square, right, is independent from this term, cosine terms, because theta is independent from a. So we can take expectation of a square separately. And then we have the rest of the term is about expectation of cosine 2 pi ft plus theta times cosine 2 pi ft. Two pi fs plus theta. This is the product of two cosine functions. So we have a formula for that. So I think here we are looking at so I forgot the exact formula, but this is a formula about cosine A. Let me just quickly Google. Times cosine B. There should be one right here. Cosine A times cosine B equals to 1/2 these two. Cosine A minus B plus cosine A plus B. Okay, you apply that formula. So here we have 1/2. This is A, this is B. So it's cosine A minus B plus A plus B, cosine A plus B. So it's cosine this guy minus this guy. So it's 2 pi ft minus s plus this one. Cosine 2 pi ft plus s plus 2 theta. Okay, looks complicated. But the nice thing is that only one of them involves theta. Right, this one matches this term. Right? Cosine 2 pi ft minus s. We have it here. And for this one, we are going to further. Oh, okay. This term is exactly the second term. Yeah. So we are exactly using that formula here. And in particular for this term, cosine 2 pi ft plus s plus 2 theta. This is another, right, something cosine A plus some B. So we can expand it. Again, using this formula. Cosine A plus B equals to this. So we can use that formula to get cosine in the first term times cosine in the second term minus sine in the first term times sine in the second term. So this term can be further decomposed into two terms. So in the end, we can completely decompose this product into this
cosine and sine terms. The motivation is to, by doing so, we can completely separate theta from all the other deterministic terms. Right? If you look at the original formula, this is deterministic. The only random is theta. But these two are involved in the same cosine function. We need to separate theta from them. So by using this cosine sine formulas, we can, in the end, we can separate theta from everything else. Okay. And then the expectation can apply to theta only, right? Applying to this term only. And these terms, they are deterministic terms. And again, we want, okay, at the same time, you can see that we want this term to be a function of t minus s, right? For being wide sense station. We want this term to be a function of t minus s. Now, if you look at this final expression, it is a second moment of A. We can, no problem. It does not involve T and S, so it doesn't matter. And this part, it is indeed a function of T minus S. So this is what we want. We want to keep this term. This is allowed in wide sense stationary. But for these terms, they depend on T plus S. And this is not allowed. It should be depending only on T minus S. Only T minus S. So we need to get rid of these T plus S terms. And again, the only way to get rid of that is to make sure these coefficients are zero. So we need expectation of cosine 2 theta and the expectation of sine 2 theta to be zero. Okay. So these are the conditions that we need in order for the random process to be wide sense stationary. Right? Turns out they are conditions on theta only, sine theta, sine 2 theta. And there are two cases that actually satisfy these two conditions. One is that theta, the phase, is a uniform distribution over the interval negative pi to pi. If that is true, you can check that these are indeed zero, these four conditions. The other thing is that theta is uniform distribution over these four discrete instances. It's either 0, pi over 2, pi, or 3 pi over 2. So both of these two can satisfy all these conditions. Okay, so we can see that this is basically, if you want to verify a random process is wide sense stationary, basically you just need to calculate this mean and the autocorrelation and check them following the definition. The mean has to be constant, meaning that it does not depend on time. Autocorrelation has to be depending on the time difference only. So the wide sense stationary is a much bigger class compared to strict sense stationary. It only requires something on the second order statistics of the random process. And consequently, to understand wide sense stationary processes, we just need to care about the time difference, right? Because the mean is constant. So if we know the mean of a random variable at any time, we know the entire mean over all times. And the autocorrelation, autocovariance function, these two only depend on time difference. So to understand the behavior of this random process, we just need to know the time difference between the random variables that we care about. And this is the same problem, so we can skip this part. Yeah. And for wide sense stationary random processes, we have the following properties. Now, first of all, it has a constant mean. By definition, there's constant mean. This is a very important property. And for the autocorrelation function, right, it only depends on the time difference. So if you want to look at the correlation between, correlation between xt plus tau and x tau, right, the random variables, I think there's a typo. This should be xt instead of x tau. If you want to look at autocorrelation between these two random variables, one is at t, one is at t plus tau. Then the wide sense stationary property says that their autocorrelation only depends on their time difference. So it's t plus tau minus t, which is a function of tau. It only depends on how far they are away from each other. I think this is a typo. This should be t, because here we have t. So it's the autocorrelation between t plus tau and t xt. And similarly, the autocovariance function is also between these two random variables. It also depends on the time difference, tau only. So therefore, for wide sense stationary random processes, we are going to denote. We can characterize the autocorrelation function and autocovariance function using only a single variable. Yeah. Because in general, for any random process, we write the autocorrelation as T and S. Right? We need to identify two absolute locations. One is S, one is T. And this is the locations of the time steps that we care about. But for wide sense stationary random process, the absolute location does not matter. All that matters is their relative locations. It's the time difference. And this is a single variable. Right? So instead of using two variables to characterize this function, we can just use one variable. Okay, so this is what we are going to use frequently. Only the input argument is only the time difference that we care about. And these are the properties of this function. First of all, this autocorrelation function is symmetric. It's an even function. And similarly for the autocovariance function, it's even function. Because Rx tau corresponds to the correlation between xt plus tau and xt. And we can switch this product, switch the order of this product, doesn't matter. You can write it as xt times xt plus tau. And this will give us the t minus t plus tau will give us negative tau. So it's the autocorrelation with the time difference negative tau, but they are effectively the same. So it has to be an even function. Now similarly for the autocovariance function, so they are even functions. And the autocorrelation at 0, well, by definition, you just plug in tau, let tau to be 0. If tau is 0, so you are looking at the expectation of xt times xt. So it's the second moment of xt has to be positive and non-negative. And similarly for the autocovariance, at 0, they are non-negative. And third property is that the autocorrelation function, right, the absolute value is bounded by the autocorrelation function at 0. And here's a short proof. Well, you write out this is the absolute value of autocorrelation. Well, you write down the definition of autocorrelation. It's expectation, right, of xt plus tau times xt. And this we have a so-called Cauchy-Schwarz inequality introduced in the previous lectures that's saying that the mean of the product is less than equal to this guy, the square root of the second product of the second moment. Okay, and these two are basically for example, this one is basically the autocorrelation at 0. And for this one, it is also the autocorrelation at 0 because it's invariant. So you get, based on the Cauchy-Schwarz inequality, the autocorrelation at 0 is the upper bound of all the autocorrelations in the wide sense stationary process. Similarly, you can do the same thing for the autocovariance function. You don't have to remember all this property, but it's just good to know. They have these nice structures. I think in the end, well, everything you have to go to the definition of this autocorrelation, autocovariance, to get the results. And the last property is saying that this is the autocorrelation function, or the autocovariance function is a positive semi-definite function. And a positive semi-definite function is defined as this is a function of two variables. So if we take such a double integration, it's always positive for any choice of functions. It's similar to the definition of positive semi-definite matrices. But imagine this is a matrix because you have two variables. So the function spans over 2 dimensions. So it looks like a matrix. And then you left multiply by A, right multiply by A. If a matrix is positive semi-definite, then this is non-negative. Right? But PSD functions basically replace the matrix multiplication by double integration. So I will skip this part. But it's just good to know that these two are so-called positive semi-definite. So these are some properties about the autocorrelation and the covariance function of a wide sense stationary process. So up to now, so this is everything about Y-sense stationary. I think most of the problems, homework problems, and final exam problems, we will be focusing on Y-sense stationary. Strict sense stationary is too restrictive, so sometimes it's too simple to understand. So we'll focus on Y-sense stationary. And up to now, we introduced the basic definitions of these two random processes, but they are just abstract definitions. We don't have too many concrete examples about these two random processes. So next, we are going to introduce a very specific Poisson process. That is an example of Y-sense stationary process. And this Poisson process is very frequently used in many applications. Especially, it can be used to model many random processes. Okay, so the construction of this Poisson process takes several steps, but in the end, it is very intuitive to understand. So let's go over this step by step. Right. And as we talked about in the Y-sense stationary random process, right? The only thing that matters is the time difference, right? So, for example, if we have if this is a time axis, and if we have a Y-sense stationary random process, now pick any two T and S, XT and XS. I consider two random variables in this random process. Now, to understand the behavior of these two, I just need to know their time difference. Once I know the time difference, I know the autocorrelation between these two. I know the autocovariance between these two. And then I basically know the second order statistics of these two random variables. Right. So the time difference is really what we care about. And that's why we first introduced the definition of increment. Right. So given a random process, we call this the increments for t greater than s. The random variable at t minus random variables at s. Because many random processes are defined iteratively. If you remember in the previous examples in the random walk, we have this iteration. Right. So this is a random walk, but x0, if we start from 0, and wk are IID Gaussian random variables. Right. So you start from 0, you generate a Gaussian number, you add it to x0, you get x1. And then at x1, you add another independent Gaussian random variable, you get to x2, right? So it's a random walk. And we will find many random processes are actually described in such a way, right? Every time the random variable in the next time is depending on the previous time in a certain way, through a certain function. So we care about the increment, right? Because in this random walk, the increment between consecutive time steps is exactly a Gaussian random variable. So the increment is exactly modeled by a Gaussian. So we call all these increments starting from S up to between S and T. And of course, this is a random variable. A random variable of a function of two random variables. So again, this increment itself is a random variable, right? Just like in this random work, the increment between these two is WK. WK is random. Each time WK is Gaussian random variable. So this is just definition. We call this increment. And then we can define an independent increment process. Independent increment process basically says that the increment between T and S, right? This is XT minus XS, is the increment between these two times, following the previous definition. An independent increment process basically says that this increment is independent from the history. It's independent of X tau for all tau smaller than S. Yeah. So basically the increment between S and the T is independent from the past. For example, in this random work, the increment xk plus 1 minus xk, well, it is wk. And the increment between k plus 1 and k is wk. The wk is independent by our construction of this random process. It is independent from the past. Why is that? Because these history random works, they only depends on wk minus 1, wk minus 2, up to w0. For example, x1 is x0 plus w0. So x1 only depends on w0. X2 is x1 plus w1. So x2 depends on w1, but x1 depends on w0. So x2 depends on w0 and w1. Okay. So in the end, all this history depends on the previous Gaussian random variables that we generated. But by assumption, wk is independent from all of them. Every time the increment that we generate is independent from everything else. So this is an independent increment process. Meaning that if you start from, suppose you are already at XS, now you want to generate the next sample pass for this random process and get to XT. Well, then the way you generate this increment is independent from the past. You don't need to care about history. This happens in many real systems, or in many cases, we make this assumption, reasonable assumption. Basically, this increment can be sort of kind of a noise in the system. And I said, okay, the noise I observed or I suffered at time t should be independent from the past. Okay. So this is called an independent increment process. The current increment in the future is independent from the past. Just technically speaking, this xt minus xs, this random variable is independent from everything, all the random variables before that. So this will make the analysis much easier because independent, then we can separate many things. And then we can define a counting process. Okay, a counting process basically, intuitively, in this process, we count. We count from 0, 1, 2, 3, 4. It's a counting process. But the way we count it is specified in this way. We start from 0. C0 is 0. Okay. At the beginning, we count 0. And then CT, this random process is non-increasing integers, meaning that the next time we increase it, it has to be 1, 2, 3, 4. It has to be integers. This non-decreasing integer values, right, continuous. Essentially, okay, this is an illustration of this counting process. At time 0, you start from 0. And you wait and wait until something happens and say, oh, I observed that event of interest and I count 1. For example, you are observing some, imagine there's a photon detector in an optic system, right? So you start from 0, and then once there's a photon hit that detector, the detector will count 1. And this is the first arrival of the photon. Right. So in this time period, no photons has arrived, so the counter is 0. And then here is 1 arrival, so we count 1. And again, we wait and wait until the second arrival, we count 2, and we count 3. Right. So this is a counting process. And this process is specified by this intermediate arrival time. Right. This is the first. This time period is the time for the first arrival of the photon, and this is the time for the second arrival, and so on. And so this is a counting process. So in this counting process, the randomness is this waiting time or this arrival time, because we are not sure about when the next photon will arrive. So that thing is a completely random thing. So these intervals could be random, but every time the counting process will add 1 to the next level. Okay, and then with all these definitions, we can define the Poisson process. So in the counting process, what is not we are not clear about this waiting time or the time of or the number of arrivals in a certain period of time. And the Poisson process provides a very, very specific description or modeling of this phenomenon. So a Poisson process with parameter lambda, we will introduce this lambda later. Right? It has to be intuitively related to the Poisson distribution with parameter lambda. Poisson process is a continuous time independent increment counting process. Well, let's forget about this statement and go to the details to better understand this process. So it is a counting process, okay, meaning that the Poisson process is basically where we are counting numbers. Okay. And the way we count these numbers is through these steps. We start from 0. We start at the beginning, we start from 0. To be more specific, so NT, you can, what is NT? Well, the Poisson process is a counting process. So NT is the integer. And this integer describes. Okay, let me put it this way. It is an integer that counts total number of events NT denotes the total number of events of interest. If you care about something, right, you just you started from time t, you start to observe, you start your observation, and you wait for the event of interest to occur. Every time it occurs, you count 1. And the next time it occurs, you count 2. Right. So NT denotes up to time t how many number of these events of interest occurs. Okay, so in that optical system, the number of photons, NT, would be the total number of photons received by that photon detector up to time t. That is the meaning of NT, the Poisson, in the Poisson process. So it counts the total number of events of interest. Right. So suppose this is time axis, and these are at these time steps, these are the occurrence of the events of interest. Right. And up to time t, now this is NT. Suppose this is t. Now up to this time, NT equals to 5, because up to this time there are 1, 2, 3, 4, 5. 5 events occurred. Right. And after here, NT equals to 2. That is the meaning of NT. Okay. So we start from 0, right? We start at time 0, nothing happens. So we start from 0. We count 0 at that time. And for all t bigger than s, the increment. Now think about this one. Suppose this is n. Okay, suppose this is s, and suppose this is t. Okay. For all t bigger than s, this is the increment, nt minus ns. So what does this mean? Well, nt denotes the total number of events occurred up to time t. Ns denotes the total number of events occurred up to time s. So the increment basically means, this is nt minus ns. This is basically means the total number of events occurred between time s and t. Right. So the increment basically denotes the increment of the occurrence of the events. How many events happens during this time? That number is nt minus ns. Okay, and this increment is independent from the past. Right? The number of occurrence of events during this time is independent from the history, independent from history. Right? For example, this could be the number of bus arrivals that you observed between S and T, and this should be independent from the past. Right? Because different buses, they are independent. They arrive at different times independently. right? So this is a reasonable assumption. The increment is independent from past. And the number 3 says that, okay, number 3 specifies how this increment is distributed. The increment follows a Poisson distribution with parameter lambda times t minus s. Well, let's look at this part. Here we want to, the Poisson process specifies that, okay, the number of events occurred during this period of time, this guy, nt minus ns, the number of events occurred during this period of time follows a Poisson distribution. Well, because this is integer, first of all, this is integer, right? So integer that counts the number of occurrence during this period of time. And for integers, we know that to model the distribution over integers, probably right, Poisson distribution is a very good choice, especially when we model the occurrence of events. We always use Poisson distribution. So the Poisson process models this increment by a Poisson distribution. Well, the Poisson distribution has a parameter, right? In this case, is a parameter lambda times the length of the interval. Okay. This lambda is the parameter of this Poisson process. Okay. You can intuitively understand this lambda as the frequency of occurrence of this event. If lambda is bigger, that means the events more likely to occur. And the Poisson process specifies that, okay, the number of occurrence during a period of time is relating to lambda and also relating to the time, the length of this time interval. And this is very reasonable because if we are counting the number of occurrence over a longer period of time, we are expected to observe more events. Right. So that's why it's a Poisson. This increment is a Poisson distribution with parameter lambda times t minus s. It depends on this lambda controls the frequency of occurrence of these events, how frequent these events may occur. And this t minus s corresponds to your observation time interval. The longer observation you take, you are expected to observe more occurrence of events. Now putting this in a precise language basically says that the probability that you observe k events during this time interval. Let's read this again. The probability that you observe k events during SMT, this time interval, is specified by the Poisson distribution with parameter lambda times t minus s. And this is the original definition of Poisson distribution, right? X equals to k takes this much probability. So the parameter lambda controls the distribution of this random variable. So in this case, in the Poisson process, parameter the effective Poisson distribution parameter is lambda times the time interval length that you are looking at. And again, this is intuitive because in Poisson distribution, we know that it has mean lambda, variance lambda, which means, right? Which means in this case, the mean of this increment, the mean of this increment means the expected number of events that you can observe during this time. It is, according to this one, the mean is basically lambda, but now our lambda is actually the Poisson process lambda times the length of this time interval. Meaning that if you are looking at the longer time interval, you are expected to observe more events. Well, and at the same time, if the events occur more frequently, if this lambda is bigger, you are also expected to observe more events during this time interval. Right. So this is how the Poisson process is constructed. You can understand it in this way. Now you start from 0, or you count 0. Right? At this time, you haven't observed anything. Right? The photon detector is reset to 0, and then you, for example, if you wait for. Sorry, is there a question? Okay, so for example, if you wait for T1 up to T1, no. Now you set up this photon detector in the optical system, and then you start to collect photons, right? And you go back to get a coffee. And at T1, you come back and check this photon detector, right? And this number of photons received during this period of time, right? This follows a Poisson distribution lambda T1. Okay. And then you get a number. This is how you specify. You get a counter on the photon detector. This is N T1. That is the reading at T1. And then you have another class. So you spend maybe 2 hours to another class. And then you come back at T2. And the reading of the photon detector is NT2. Okay. Now these two, the difference of these two, right, models the number of photons that we received during this period of time. This follows Poisson distribution lambda T2 minus T1. Okay, and then this keeps going on, right? So you specify this process by this kind of increments. Yeah. So it is a independent incremental process. It is incremental. We are counting the number of photons incrementally, and every time, every increment is independent from the past, right? Because intuitively, the number of photons that you received during this period of time should be independent from the past. You can also use this process, right, to model. If you are standing at a bus station and observing the bus arrivals, you can model the number of bus arrivals that you observe along the time axis. It is exactly a Poisson process. The lambda controls the frequency of occurrence of the events, and And these are the technical tools that we will use to analyze the pausing process. In the homework, you will see many examples. Basically, we understand this process by increments. We decompose it by into a bunch of increments. Each increment is a Poisson distribution. And among these increments, they are independent. So this makes the analysis a lot easier. And this process is actually many real life events are modeled by this process, like photon detectors we just mentioned, and also the phone calls that the phone calls to a telephone switch center. Right? The phone calls received, phone call requests received by a by a server, right? Or the packet demands to the internet servers. Right? These are counting processes. We are counting the number of photons, number of phone calls, number of packets over time. And during a period of time, the number of events is modeled by a Poisson process. And there are some other characterizations of Poisson processes. Okay, so here we understand this Poisson process in terms of time intervals. We pick a time interval, and we ask, okay, how many events do we observe during this time interval? And that is specified by a Poisson distribution. Now, we can also ask the other question. What is the inter-arrival time between the I-1 and I's arrival? Or here, the arrival means the occurrence of the events. For example, these are the occurrence of events, and this is I's event, this is the I-1, and this is I's event. So instead of looking at the intervals, so looking at the intervals time intervals is one way to understand this Poisson process. The other way to monitor this process is to focus on the occurrence of the events, right? Once I know the occurrence of these events, I can just count NT. Basically, I just pick a T and count how many occurrence do we have up to time T. So the other way to understand Poisson process is to look at the occurrence of events, and we call the inter-arrival time between I-1 and I's event. We call this tau I. Okay. For example, this is okay, zero's event 1, 2, and this is tau 1, the arrival time for the first event, right? And this is arrival time for the second event, and they are random, right? Because you don't know when will the next event happen. So these tau i's, they are random. And the question is, what is the distribution of tau I? What is the distribution of tau I? And this is how we. This is an interesting perspective. We can look at, for example, if we look at tau 1, the arrival time of the first event. You start your observation and you wait until the first event occurs. This is the tau 1. We look at the probability that the first event occurs after U, okay, tau 1 bigger than U. And think about think about that. If tau 1 is bigger than u, that means the first event occurs after time u. Tau 1 bigger than u equivalently means that the first event occurs after time u. If the first event occurs after time u, that means up to time u, my counter is still 0. Because the first event comes after u. So after time u, my counter should be 0. That equals to probability that nu equals to 0. And because n0 is 0, the starting point of the counter is always 0. So this is equivalent to nu minus n0 equals to 0. Why do we want to do this? Because for Poisson process, we know how to specify this increment, right? The increment we are given in the original description of Poisson process, the distribution of the increment is given. So we translate the inter-arrival time into the increment. So the first arrival time bigger than u, meaning that up to time u, the counter has not observed anything. And we know this follows a Poisson distribution with lambda times the interval length u. So this probability is given by Poisson distribution at realization 0. So you plug in this to the Poisson distribution, you get this number. So in the Poisson process, the arrival time, the probability that the first arrival time is bigger than u takes this exponential form. Right? With this, you can derive a CDF function. Once you have a CDF function, you have the PDF. But it looks like it is an exponential random variable, exponential-like random variable. And the same argument applies to tau I, right? If you want to look at the tau I, okay, let's quickly write it down. If you look at tau I can look at tau I, probability that tau I is bigger than u. Meaning that the ice event occurs after time u, right? Tau I greater than u, meaning that ice event I think this should be, no, tau I only characterizes the increment. So the ice event is the occurrence of the I minus 1 event plus tau I. Yeah, so I think, for example, tau I should be the probability that, let's denote the I minus 1 event is so the ice event, which is tau 1 plus tau I, I think this should be derived in a incremental way. If we have, once we have tau 1, we can look at tau 2. Yeah, because tau 1 plus tau 2 is the occurrence of the second event. Oh, I think there's a simpler argument. So I think all these taus, yeah, okay, all these taus, they follow the same distribution. Yeah, they should follow the same distribution because it is an independent increment process. So the increment, this guy tau 2 has nothing to do with previous, right? Tau I has nothing to do with previous occurrence of events. So you can imagine this. To get tau I can imagine that I reset the counter at this time. Yeah, just reset my counter. Ignore the history. I just reset my counter, and I'm looking at the next event. And this would be the first event after resetting the counter. Yeah. So everything goes back to this case. So basically, all the inter-arrival time in this Poisson process, all the inter-arrival time of the events follows this exponential distribution. And you can check that this one will give you a PDF that in the form of exponential distribution. Okay. So this is another interesting perspective to understand Poisson process. By looking at the occurrence of these events. So every occurrence, first occurrence following the exponential distribution. And once you observe that, and then waiting for the next occurrence, this one again follows this exponential distribution. So this is different from our first description of the Poisson process. Here we just pick an arbitrary time interval and see how many events are in there, and that number of events follows this Poisson distribution. These are two different ways to describe this process. And we can look at the second order characterization, that the mean autocorrelation function, right? These basic statistics of this Poisson process. Now, first of all, we can look at the mean of NT. NT is the number of occurrence up to time t. And because N0 is 0, so we can equivalently, we look at this increment, right? Always look at increment if we are looking at the time intervals. And this increment we know follows the Poisson lambda t distribution. So we know the expectation is lambda t. And you can see that in the Poisson process, the mean is not constant. It's not constant. So it is not a wide sense stationary process. And looking at its autocorrelation function, right? Basically, expectation of NT times NS. We assume T is bigger than S. Okay, and this is the interesting part. This is the trick that we are going to play a lot in the Poisson process. We need to somehow, right, transform the product into increments. Because everything, like if we care about this NT, always look at the increment. So we keep this NS term. For NT, we minus NS plus NS. Right? This is 0. So it's basically NT times NS. But we introduce these two terms. And then we distribute this to ns. So we have this increment times ns plus ns square. So that gives us these two terms. The nice thing about introducing this increment is that we know by the Poisson process, the increment is independent from the past. Right? So this is independent from ns. So by independence, we can separate them. And this one, we know is, this one follows Poisson lambda t minus s distribution. This one follows Poisson lambda s distribution. Now, what about this second moment term? This is the second moment of ns. It is basically the variance plus the square of the mean. And these two statistics can be calculated because why? Because ns so ns square equals to like ns minus n0 square. N0 is 0. Okay? So this random variable we know is Poisson lambda s. So we know the variance and the mean. The mean is given here. Okay, putting everything together. This one, the mean is the mean of this Poisson distribution. So lambda times t minus s. This one is the mean of this Poisson distribution. So it's lambda s. And this second moment is the variance plus mean square. The variance of Poisson distribution is lambda s. The variance of this ns, ns follows Poisson lambda s distribution. As the variance is this one. Mean of this Poisson distribution is lambda s. So it's lambda s to the power of 2. And you simplify everything, you get this one. Right, so this is the autocorrelation function. When s is less than t. And when t is less than s, this one will be replaced by t. So in general, the autocorrelation takes this form. Okay, you can directly leverage this formula. This is autocorrelation, and this is the autocovariance. Autocovariance is the autocorrelation subtract the product of the mean, and it turns out that the product of the mean is this one. So this is the autocovariance covariance function. So this shows that Poisson process is not wide sense stationary, but it has so many nice properties that can actually model a lot of real life phenomena. Okay. So you can directly utilize these formulas in the homework, but you can see that in many cases, you will play this trick, introduce the increment to analyze the Poisson process. Because the Poisson process is originally specified in this way, through the increments. The increment is independent from the past. So that's why we start from the product and then introduce this increment. Okay. And this is another characterization of the Poisson process. We are looking at the distribution of this event. What is this event? The probability of this event. What is this event? Up to time t1, we observe k1 events. Up to time t2, we observe k2 events. And up to time tn, we observe kn events. We need to calculate the probability that this one. And the way we do this is, again, translate this into increments. Here we assume that T1 less than T2, so the timestamps are increasing, and of course, because of that, K1, K2, they are also increasing. Because this interval T2 covers T1, right? So the counter has to be increasing. This is equivalent to say that, okay, I start from 0 and up to T1, I see K1 events. And then between T1 and T2, I see K2 minus K1 events. Okay. Right. This perfectly describes the total number of events that we see at T2. We look at this in an incremental way. And then between Tn minus 1, we observe this many events. Right? They are equivalent. It's equivalent to say this. And because all these increments, now we are looking at these are all increments. Even the first one is increment. It's increment from 0 to T1. So all these increments, they are independent according to the Poisson process. So we can just the probability of this joint event is the product of the probability of the individual events. And just look at the product of the probability of each event. Now each event corresponds to that during Ti minus 1 and Ti, we see this many events. And this exactly follows the lambda Ti minus 1 Poisson distribution. And then you just multiply all these different Poisson distributions together. Each one you plug in different integer. So this is what you get in the end. Okay. So this is the distribution. This is the distribution of the counters of okay, let me put this. This is a distribution of the readings of the counter at different time steps. Right. I'm looking at the reading of the counter at time T1, T2, and Tn, and their readings are K1, K2, and Kn. And this is the probability that this happens. And we just have the next thing is about sum of independent process, independent Poisson process. It's basically that we now have two Poisson process, N1T and N2T, each one with parameter lambda 1 and lambda 2. Okay, so we are looking at two different types of events, right? Each one may occur with a different frequency. Now we look at the total sum of these two random processes. And this is again another random process. And this result is to say that intuitively this NT is also a Poisson process with the parameter lambda equals to the sum of these two individual, these two parameters of these two individual Poisson processes. So I will sketch the proof. Okay, sketch the proof. The first two conditions are easy to check. So the counter at 0 is also 0 because for the two individual Poisson process, their counters are 0 at the starting point. And then we can argue that this NT is an independent increment process. Let's just assume that the key point is to how to verify that the increment of this NT process is indeed a Poisson distribution. We can just quickly look at that. So we are looking at the probability of the increment of this combined, right? Let's call this combined Poisson process. So NT minus NS equals to K. So this is the total number of events that occurred during this period of time. And this total number of events includes the events that occurred in the first Poisson process, as well as the events occurred in the second Poisson process. Right? So basically, NT equals to N1 plus N2. So basically, this is the sum of the total events occurred up to time t, and this is total events occurred up to time s. And because it involves two different Poisson processes, N1 and N2, so we combine N1 together, we combine N2 together. Okay, just rearrange the terms. And this is the increment of the first Poisson process. And this is the increment of the second Poisson process. Now, this is to say that, okay, the sum of these two increments must be K. And this will cover many different cases, right? It could be that the first increment is I and second increment is K minus I. Well, this I can be taking different values from 0 to K. This is all different possibilities. Right, so this event is equivalent to the sum of all these events. And they are destroying the events. So by the probability law, we can have a summation here. Okay. And then these two, they are now independent because this is everything about increment of first process. This is the second process. They are independent. So we can calculate their probabilities, the product of their individual probabilities. And then this is given by a Poisson distribution with parameter lambda 1 times t minus s, because this is about the first Poisson process. There's lambda 1 and the time interval is t minus s. And we are looking at I. There are I events in this process. And in the second random Poisson process, it is with parameter lambda 2 times t minus s. And we are looking at K minus I. Okay. And there's a summation outside. Okay. The rest of the scene, I will not go over that. You can double check yourself. Is simplify this summation. And in the end, you do get a Poisson distribution. You do get a Poisson distribution where lambda is lambda 1 plus lambda 2. So you can check that. So this is to say that if you sum up two Poisson processes, it is still a Poisson process. A very, very nice property. But of course, they have to be independent. If you sum up two independent Poisson processes, they are independent. And the last one is to, instead of summing up, we split a Poisson process into two How do we split that? Well, suppose NT is a Poisson process with parameter lambda. This is how we split the Poisson process into two. For each occurrence of the event, right? For each occurrence of these events in this Poisson process, we will independently assign each event to either the counter N1 or the counter N2. Okay, so basically, now suppose these are the occurrence of the events, right? And you use in this Poisson process, we use NT that counts all this, the total number of all these events, right? Now we can split this into two. So for each event, I have two counters. I now create two counters, N1 N1T and N2T. Each event has probability P to go to this counter and has probability 1 minus P go to this counter. It's a Bernoulli distribution. And I do this for every such event, independently. Right. In this way, these two counters will receive different numbers. And N1 plus N2 equals to these two always equals to NT. Because every event either goes to this one or goes to that one. So the sum of these two is the total number of events. So this is how we split NT into these two using a Bernoulli model. And so each event independently is selected to go to N1 or N2 with probability P and 1 minus P. Then we can show that these two are independent Poisson process with parameter P lambda and 1 minus P lambda. Okay, again, very intuitive answer. Because that's how you split them with probability P and 1 minus P for each event. But we will need to check. We will need to check this result. It's a short proof, so let's go over that. So we look at the probability of this one, that the counter 1 receives up to time t receives k events. Counter 2 receives n events, right? And because the sum of these two counters equals to NT, so I can just this is equivalent to say I keep these two events here, right? And additionally, I add this one, but this is a redundant event because given N1 and N2, for sure I know that the total number of events is k plus m. Right? The total number of events is k plus m. So they are the same because this is redundant. Okay, and then for this probability, I expand it using the conditional probability. Right? So probability of this NT equals to k plus m times the probability of these two given conditional this one. Conditional. This is standard conditional probability. The reason that we do this is that is because this is simple to calculate. Everything is simple to calculate. This one is basically the Poisson, because we know, right, the original process is a Poisson process. So this is exactly given by this Poisson distribution with parameter lambda t. because for now what we only know is that NT is a Poisson process, right? We haven't proved anything about these two guys, right? So we have to introduce this one so that we can calculate this part using the Poisson process, Poisson distribution. And this part, although we don't know about this distribution of N1 and N2, but this conditional distribution turns out to be very simple. Because if you look at this conditional distribution, we are given that in total, we observe K plus M events. Now, what is the probability that the first counter receives K, second counter receives M? Well, because the way we assign these events to the counters following a Bernoulli distribution, right? So this follows the binomial distribution. So this is like, okay, in total, you have K plus M events. Now you choose K and goes to counter 1. Now, what is the probability of doing that? Well, every time you send it to the counter 1, it's probability P. So it's P to the power of K. For the rest of the events, they have to go to the second counter. So it's 1 minus P to the power of M, right? So this happens to be a binomial distribution. And then the rest of step is to simplify the terms, and I will skip this part. But in the end, you can rearrange the result into a product of these two. This is one term, and this is the second term. But look at each term. It is exactly the, for example, the first one, you have K, right? This is exactly this K here. The second one, you have this M. It's exactly this small m here. And the first one is exactly given by a Poisson distribution with parameter P lambda. The second one is given by Poisson distribution with parameter 1 minus P lambda. Okay. So these two shows that indeed these two counters, they are Poisson, the Poisson process. And because they are taking a product form, so they are independent. They are independent. So somehow this binomial distribution can decompose this the overall Poisson distribution into two smaller Poisson distributions. Yeah, this is where the magic happens. Okay, so this is the splitting of the Poisson process. So basically, it is all these results are very intuitive to understand, but they are not that trivial to show. So I will skip the last part. It is not required in the final exam, but it basically characterizes the following distribution. So given that up to time tau, we observe, okay, given that up to time tau, we observe n events, right, in the Poisson process, I want to look at the distribution of the occurrence of these events. If I given condition on this event, right, up to time tau, we observe n events. But where are they? Where are those events? We are interested in the occurrence of these events. This T1, we want to know the distribution, the PDF of the occurrence of these events. Okay. And turns out that this is a uniform distribution between 0 and tau. You can see this PDF density has nothing to do with T1, T2, and Tn. It's a uniform distribution. Right, so this is also kind of intuitive. Given that we observe n events, up to time tau. The occurrence of these events happen to be uniformly distributed over the time interval. And again, this is the Poisson process, but it happens to be uniform. So I will skip the proof, but you can refer to this section in the book for the details of the proof. Okay. Yeah, I think that covers everything about the Poisson process, and it will be the final exam and the homework will be related to this. So please also look at the video that I uploaded to the YouTube channel on the homework 12. In homework 12, we have several problems on how to analyze the Poisson process. Okay. So that is everything about this course. So if you have any questions about homework, feel free to. So I will be here in the afternoon from 3 to 6. And feel free to schedule a meeting with me before the final exam at any time. And don't forget to take this cross feedback survey. Okay, I think that is everything about this course, and it's a great semester. Thanks everybody for taking this course, and good luck to the final exam. I will see you next. It will start next Wednesday, Tuesday.
Thank you. Have a good day.
Yeah, see you guys. Have a nice day.